If you look into the bowl of a silver spoon, your face stares back at you completely upside down. But if you glance at the passenger side mirror of a car, it squeezes 3 lanes of traffic into a tiny upright square of glass. To understand why this happens, we have to start with flat mirrors. The standard rule of light is that the angle it hits a surface will exactly match the angle it bounces off. We measure this against an imaginary perpendicular line called the normal. Finding a 90-degree perpendicular line on a flat surface is simple, but what happens when the surface is a sphere or a bump? Where does that normal line sit when the glass is curving away from you? Calculating that perpendicular line on a curve is what allows us to predict the bounce. Once you can find the normal, you can trace exactly how these mirrors warp, flip, and shrink the image. Imagine a flat piece of rubber foam. If you stick a row of pins straight down into it, those pins represent our normal lines. Because the foam is flat, the pins are parallel, meaning light rays would bounce off in the same direction they arrived. But bend the edges inward to make a bowl shape, what we call a concave surface, and the geometry changes. All those pins, or normal lines, are now forced to point toward each other, intersecting at a single point in the center. If you flex that same material outward into a dome, creating a convex surface, the opposite happens. The normal lines fan out, spreading aggressively away from one another. The curve acts as an infinite collection of microscopic, angled flat mirrors. Each tiny section strictly follows the law of reflection, but the changing angle of the surface directs the light in a new direction. To navigate a curved mirror, we map its space. The exact center of the glass is the pole. The straight horizontal line cutting through it is the principal axis. And if you imagine the curve as a complete sphere, the middle of that sphere is the center of curvature. This diagram shows the focal point. When parallel rays of sunlight hit a concave mirror, the curved geometry forces all of them to reflect inward, where they meet precisely at this single dot, marked F. We don't need to trace millions of rays to figure out what an image will look like. By drawing a ray diagram using just 2 or 3 predictable paths starting from the tip of an object, we can map exactly where an image will form. Looking at this diagram, we have a candle placed far away from the mirror, well past the center of curvature. The light rays reflect and intersect below the axis, creating an image that is smaller and completely upside down. But look at the path of the light when the candle is moved extremely close to the glass, past the focal point. The reflected rays spread apart. They diverge. They will never meet in front of the mirror. Because the physical light is scattering, our eyes trace those diverging rays backward through the glass. They appear to intersect behind the mirror, forming a massive, upright, virtual image. Pushing an object a few inches across a focal point changes the entire outcome. It determines whether the reflection is shrunk or magnified, upright or inverted. This diagram shows a convex mirror. Here, incoming parallel rays hit the outward bulge and immediately scatter. If you trace those reflected rays backward, they all appear to originate from a focal point hidden deep behind the glass. This scattering is exactly how a convex mirror captures a massive, wide-angle view of the world and compresses it into a tiny reflection. This creates a physical boundary. A real image happens when light rays actually converge in physical space. You could project it onto a piece of paper. A virtual image cannot be caught on a screen because the light rays never actually meet. Virtual images only exist because our brains assume light travels in straight lines. We perceive a physical space behind the mirror that is entirely a construction of our own perspective. This graphic shows the mirror formula. Looking back at the ray diagrams we've been drawing, you can see triangles forming between the object, the mirror, and the focal point. By using the geometry of these similar triangles, we can reduce those lines into this single equation. Right beside it is the magnification equation. Dividing image distance by object distance tells you exactly how shrunken or enlarged the image will be. To make the math work, we use a sign convention. Any distance measured against the direction of the incoming light is recorded as a negative number. This acts as the grammar that keeps the algebra consistent. Formulating these rules meant humans no longer had to rely on trial and error to shape glass. We could calculate exactly how to move light before the mirror was even built. If you place a small halogen bulb directly at the focal point of a concave mirror, The curve catches that light and throws it forward in a powerful, perfectly parallel beam. This is how car headlights pierce the dark. Consider the large convex mirrors in store corners. Their diverging geometry scatters light outward, providing a wide-angle view our eyes couldn't naturally capture. When we map how a curve directs light, we gain the ability to control it. Understanding these specific points on a sphere is what allows us to build the visual tools that define the modern world.